ever wondered what lies beyond the event horizon? That point of no return where even light gives up? What if the most mysterious objects in the universe aren't just cosmic vacuum cleaners, but gateways to unimaginable physics or even other dimensions? In this video, we're plunging into the heart of the cosmos to explore 10 mind-bending truths about black holes. What really happens inside, what bizarre phenomena they create, and how they challenge the very laws of physics as we know them. From the terrifying concept of spaghettification to the strange idea of white holes, and the possibility of black holes being cosmic information keepers, get ready to have your understanding of space and time fundamentally And trust me, the #1 revelation about what might exist at a black hole's core will leave you absolutely speechless. You're about to delve into extreme gravity, warped space-time, and theories that push the limits of human imagination. Can you imagine a place where time itself comes to a standstill? Stick around, because I'm going to reveal how black holes twist the very fabric of time. Before we embark on this cosmic dive, do me a quick favor, hit that like button, share this with a friend who loves the mysteries of the universe, and if you haven't already, subscribe and ring that notification bell so you don't miss out on more mind-bending content from 360 World. And I want to hear from you. What's your wildest theory about black holes? Drop your thoughts in the comments below. 10. The event horizon, the point of no return. What is the true boundary of a black hole? Imagine an invisible boundary surrounding a black hole, a cosmic threshold from which nothing, not even the fastest light particle, can escape. This isn't a physical wall. It's the event horizon, a terrifying point of no return that defines the very edge of a black hole's influence, and understanding it is key to grasping what's truly inside. Why is this boundary so absolute? The event horizon is a spherical boundary in space-time where the gravitational pull of the black hole becomes so immense that the escape velocity exceeds the speed of light. Anything that crosses this boundary matter energy, information is irrevocably pulled towards the singularity at the center. From an outside observer's perspective, objects approaching the event horizon appear to slow down, dim, and eventually freeze and fade away, never truly crossing over. However, for the object itself, it crosses the horizon in a finite amount of its own proper time, unaware of the point of no return, until it's too late. It represents a fundamental limit of our observable universe, a one-way cosmic street, a point of no return from which nothing can escape. What do you think it feels like to cross it? Let me know in the comments. Embrace yourself, because our next concept is a terrifying consequence of crossing that boundary. Night spaghettification, the ultimate stretch. Imagine being stretched like a piece of spaghetti by an unimaginable cosmic force. If you were to fall feet first into a black hole, the gravitational pull on your feet would be astronomically stronger than the pull on your head, literally stretching your body into a long, thin strand before you even reach the singularity. This horrifying phenomenon is called spaghettification, a real and inevitable consequence of extreme gravity that defies anything we experience on Earth. How does gravity act so unevenly? Spaghettification, or the noodle effect, occurs because the tidal forces of a black hole become incredibly extreme as you approach it. The difference in gravitational pull between 2 points on an object, even if they are only a few feet apart, becomes so vast that it would rip anything apart. For smaller, stellar mass black holes, spaghettification would occur long before you even reach the event horizon, turning you into a stream of atoms. For supermassive black holes, the tidal forces are less extreme at the event horizon, meaning you could cross it intact, only to be spaghettified moments later as you approach the singularity. It's the ultimate cosmic shredder, a vivid illustration of gravity's terrifying power. The ultimate cosmic stretch. What do you think would be the last thought before being... Don't go anywhere, because our next mystery involves a bizarre, theoretical opposite of a black hole. 8 white holes. The cosmic Could there be objects in the universe that are the exact opposite of black holes? Imagine a theoretical region of space-time that nothing can enter, from which only matter and light can escape, pushing everything away. This isn't a black hole, it's a white hole, a concept that arises from Einstein's equations. but remains purely hypothetical. A bizarre cosmic expeller that would defy our understanding of how things enter and exit the universe. Do white holes really exist? White holes are theoretical objects that are mathematically allowed by Einstein's theory of general relativity, essentially representing the time-reverse version of a black hole. While a black hole is a region from which nothing can escape, a white hole is a region into which nothing can enter from the outside, but from which matter and light burst forth. They are often discussed in the context of wormholes or as remnants of the Big Bang, perhaps even connected to black holes on the other side. However, unlike black holes, no observational evidence for white holes has ever been found, and many physicists believe they are purely mathematical curiosities, unable to form naturally in our universe. Still, their theoretical existence forces us to confront the deepest questions about the origins and endpoints of cosmic phenomena. A cosmic geyser spitting out matter, if they exist, what would they look like? Up next, a strange phenomenon related to light and black holes. 7. Gravitational lensing. Black holes as cosmic magnifying glasses. Have you ever thought of black holes as giant cosmic magnifying glasses? Imagine light from a distant galaxy being so profoundly bent and distorted by the gravity of an unseen black hole in between us that it creates multiple, stretched, and incredibly bright images of that faraway galaxy. This isn't just an optical illusion, it's gravitational lensing, a powerful phenomenon predicted by Einstein and used by astronomers to see the invisible mass of black holes, revealing their profound impact on the fabric of space-time. How do black holes warp light so dramatically? Gravitational lensing occurs when a massive object, like a black hole or a galaxy cluster, sits between a distant light source and an observer. It's immense. Gravity acts like a giant lens, bending the light rays from the background source. This can result in multiple images of the same distant galaxy, or even a distorted ring of light around the lensing object. This phenomenon is a direct confirmation of Einstein's theory of general relativity, which states that massive objects warp space-time and light follows the curvature of this warp space. Astronomers use gravitational lensing to detect and measure the mass of otherwise invisible black holes and dark matter, providing invaluable insights into the distribution of mass in the universe. It's a remarkable way to perceive the invisible. Black holes as invisible lenses. What else could they be bending or distorting that we can't see? Don't go anywhere, because our next mystery involves what happens to information when it falls into a black hole. 6. The information paradox. Is data really lost forever? Can information truly be destroyed in the universe, or does it always persist? Imagine throwing a book, or even yourself, into a black hole. According to our current understanding of physics, all the information contained within that object, its quantum state, its history seems to vanish from the universe, violating one of quantum mechanics' most fundamental principles. That information can never truly be lost. This is the black hole information paradox, a profound theoretical conflict that has puzzled the brightest minds in physics for decades. Where does the information go? The information paradox arises from the apparent contradiction between general relativity and quantum mechanics. Stephen Hawking famously proposed that information is indeed lost, but later revised his theory, suggesting it might be scrambled or encoded in the radiation that black holes emit. Other theories suggest information is stored on the event horizon itself, or that black holes act as holograms encoding all their swallowed information. Resolving this paradox is crucial for developing a unified theory of quantum gravity and remains one of the most significant unsolved problems in theoretical physics, challenging our understanding of reality itself. A cosmic riddle about the very nature of information. If information isn't lost, where is it truly stored? Coming up next, a bizarre idea about the hearts of black holes. 5 wormholes, black holes as cosmic shortcuts. Could black holes be secret cosmic shortcuts to other parts of the universe, or even other times? Imagine the extreme curvature of space-time around a black hole bending so dramatically that it creates a theoretical bridge or tunnel connecting 2 distant points in space-time, allowing for rapid travel across vast distances or even through time. This isn't just science fiction. It's the concept of wormholes, a fascinating but highly speculative idea that arises from black hole physics, suggesting potential cosmic doorways. Are these shortcuts real? Wormholes, or Einstein-Rosen bridges, are hypothetical tunnels through space-time that could theoretically connect two separate points in the universe. While they are a direct consequence of general relativity equations, and black holes are often seen as potential mouths to these tunnels, stable and traversable wormholes would require exotic matter with negative energy density to keep them open. Even if they exist, the immense gravitational forces and radiation would make passage incredibly dangerous, if not impossible. Despite the practical impossibilities, the mathematical possibility of wormholes continues to fascinate physicists, pushing the boundaries of our imagination about cosmic travel and connectivity. Cosmic tunnels too. What would you do if you found one? Don't go anywhere, because our next mystery involves black holes growing to unimaginable sizes. 4. Supermassive black holes, the universe's architects. What if the largest black holes aren't just destructive forces, but are actually crucial architects of galaxies? Imagine black holes millions or even billions of times the mass of our sun, residing at the centers of nearly every large galaxy, influencing the birth and death of stars and the very structure of the cosmos. These aren't just big, they're supermassive black holes, and their profound role in galactic evolution remains a puzzling, active area of research. How do they grow so incredibly large? And why are they so essential to galaxies? Supermassive black holes are the giants of the black hole family, with masses ranging from hundreds of thousands to tens of billions of times that of our sun. Almost every large galaxy, including our own Milky Way, appears to have an SMBH at its core. Their growth mechanism is a major astrophysical mystery. They grow by accreting vast amounts of gas and dust, and by merging with other black holes during galaxy collisions. What's even more puzzling is their fundamental connection to galaxy evolution. The size of a galaxy's central bulge is directly proportional to the mass of its central SMBH, suggesting a coevolutionary relationship where the black hole influences star formation and galactic structure. Understanding how they form and grow so rapidly in the early universe remains a significant challenge, making them active, powerful, and mysterious drivers of cosmic evolution. Cosmic giants shaping entire galaxies. What does their existence tell us about the hidden order of the universe? Now, prepare for the top 3, which delve into the most mind-bending aspects of black holes. The next one is about what would happen if you entered a rotating black hole. 3 ring singularities, a path through a rotating black hole. Could falling into a black hole not mean instant destruction at a single point? Imagine that if a black hole is rapidly rotating, its singularity doesn't collapse to an infinitely small point, but instead stretches into a bizarre, one-dimensional ring. This isn't just a mathematical quirk. It's a ring singularity, a theoretical concept that suggests a path through a black hole might actually exist, potentially leading to another universe. Is there really a way to avoid the crushing singularity? For non-rotating black holes, all matter is crushed to an infinitely dense point singularity. However, for rotating black holes, general relativity predicts that the singularity is smeared out into a one-dimensional ring. This ring singularity means that if an object were to fall into a rotating black hole and somehow avoid the ring, it might theoretically pass through the black hole's interior without hitting infinite density. While the environment would still be incredibly extreme and dangerous, this concept raises the speculative possibility of bifurcated universes or connections to other regions of space-time, often linked to the idea of. It's a highly theoretical but mind-bending consequence of black hole rotation that challenges the simple point of no return narrative. A rotating black hole might have a secret passage. What lies beyond such a bizarre cosmic gateway? Up next, a chilling theory about black holes and our universe's beginning. 2. Black holes as seeds of new universes, the multiverse connection. What if every black hole isn't an end, but a beginning? Imagine that the singularity inside a black hole, instead of just crushing matter out of existence, acts as a seed for the creation of an entirely new, infant universe, perhaps bubbling off from our own like a cosmic branch. This isn't just theoretical, it's a multiverse hypothesis where black holes birth new universes, a mind-boggling concept that links the largest cosmic destroyers to the very fabric of cosmic creation. Could our own universe have been born inside a black hole? This fascinating, albeit speculative, theory proposes that when matter collapses into a black hole, it doesn't simply disappear. Instead, the extreme conditions within the singularity could trigger a Big Bang in a new, distinct region of spacetime, essentially forming a baby universe. From our perspective, the matter vanishes into the black hole. From the perspective of the new universe, it's just beginning. This idea connects black holes to the concept of a multiverse, where countless universes are constantly budding off from one another. While currently untestable, it's an elegant solution to some of the deepest cosmological puzzles, such as the initial conditions of our own universe, suggesting a continuous cosmic cycle of death and rebirth. Black holes as cosmic wombs, a truly profound idea that redefines destruction as creation. And now, for the number one truth about black holes that will truly make you question reality itself. This is the one that changes everything. 1. The holographic universe and black holes. Is our reality a projection? What if our entire universe, including you and me, is just a 3D projection of information encoded on a distant 2D surface? Imagine that the principles governing black holes, specifically how they store information on their event horizons, hint at a fundamental cosmic truth that our seemingly solid three-dimensional reality might actually be a hologram, a vast, complex projection from a lower dimensional boundary. This isn't just a theory, it's the holographic principle, a revolutionary concept inspired by black holes that could redefine the very nature of existence. Are we living in a cosmic illusion? The holographic principle emerged from physicists' attempts to reconcile general relativity and quantum mechanics, particularly concerning black holes. Jacob Bekenstein and Stephen Hawking showed that a black hole's entropy is proportional to the area of its event horizon, not its volume. This suggests that all the information about what falls into a black hole is encoded on its 2D surface rather than within its 3D interior. Extrapolating this to the entire universe, the holographic principle posits that the information describing our 3D cosmos could be encoded on a distant 2D boundary. While it sounds like science fiction, this principle offers a potential way to unify physics and explain certain quantum phenomena. It suggests that our perceived 3D reality, including gravity, might emerge from more fundamental, two-dimensional information, making our universe a giant cosmic hologram. Our universe, a giant hologram projected from a black hole's principles. It's the ultimate mind-bender, isn't it? If these mind-boggling insights into black holes left you craving more cosmic mysteries, then you absolutely have to check out our next video right here, where we explore even more bizarre, astronomical phenomena that defy current scientific understanding. You won't want to miss it. And remember, if you only scroll to the end of this video, you missed out on the chilling concept of spaghettification and the potential for wormholes. Definitely go back and watch those parts. Before you go, hit that like button one last time. Share this video with anyone who loves to ponder the universe's deepest secrets. And if you haven't subscribed yet, what are you waiting for? Join the 360 World community and let's keep exploring the cosmos' most astounding secrets together. Until next time, stay curious, stay questioning, and keep looking up.